come and take one. There's 2 over here and 2 over there. So the operating system of the day is called Multics, and Multics is a pretty important operating system in history because it's the predecessor of actually Unix. So this one plays a pretty big role in where OSs have come from. And what it stands for is Multiplexed Information and Computing Services. Horrible name. And it's out of MIT, and it was released quite a long time ago. So this came out in 1969, and it ran on both GE and Honeywell machines. And this operating system was the first to do many, many things. So it has a single level storage, which means that they are going to actually use files and for regular memory operations. So they treat everything like a file, which is something that even in Linux today we still do. You want to talk to a device? Say something attached to the serial port? Well, that's dev TTY1, which is a pretty cool idea. Multics also had things like dynamic linking, so you can actually link libraries into your program while they were running, which was a pretty cool thing. And one of the weirdest things about Multics is the ability to reconfigure the hardware without rebooting the OS. What that means is kind of like plug and play. You want to attach new storage or remove existing storage? Well, you just do it, and you don't have to reboot the OS so that it can figure out what's going on. That's a pretty cool feature. Now, they also took it to a bit extreme. My understanding is that if you had a multi-CPU system, you could actually disconnect a CPU while the OS was running, and it would be totally fine with that. Don't do that. Generally speaking, this is a feature that has come up through from Multics into modern operating systems, but we don't offer plug-and-play kind of features for everything. For example, you can do plug-and-play keyboards and mice and external peripheral devices and so on, but don't, while your computer is on, reach in and pull the network card out. That's a really bad idea. Not just from the operating system's perspective, but because you're going to get shocked. And if you're wondering why I know this, is because I did it once. Yeah, don't do that. Don't pull cards out of your computer while it's on. The shock is almost as bad as an electric fence. If you haven't experienced that, don't go out and find out. We also in Multics had the idea of security really come into play. They had this idea of rings of security, which is kind of like their logo, where if you're in the innermost secure ring, that is, you have the most permissions to do things, and as you work your way into outer rings, you have less and less permission. And when we talk about processes in virtual memory, you can see what exactly we're referring to by permission. And it also had things like command processors as a user application this time, instead of actually being part of the kernel. So that's things like shells. And again, Multics, that's Unix's predecessor. And in fact, Unix was actually developed by some of the same people that are behind Multics, which is kind of cool. All right, so in terms of announcements, of course, you have assignment 1, which I believe is due on Monday. And I highly recommend that you don't use the slip days on it. I know with the traffic simulation problem, it's going to be ever so tempting to use some slip days to get inside of those metrics that we want you to. It's not worth it. Yes, I know it's marks. But what you're going to see is when we actually give you A2A and A2B, which I know are already posted to the website, A2A is a debugging nightmare. Theoretically speaking, the code is not that hard, but you have to think of things like race conditions and synchronization, and that actually sinks a lot of people's battleships. And they'll spend, one afternoon writing the code, and then they spend, 3 weeks trying to debug it. Save your slip days for A2A. The traffic simulation after A1, we don't care. There's no traffic light in an operating system. This is just a silly simulation we put in the kernel of the OS so you could get some experience with synchronization before you actually did some real synchronization within the kernel. So if it doesn't work on A1, it's not going to matter for A2A or A2B or A3. But if you don't get A2A working, it really matters for the remaining assignments. So Save your slope days if you can. All right, it's due on Monday. We're going to give you a few more hints about how to do A1 today. And might as well do that now. Why not, right? So we've gone over already locks and condition variables in class. And all of the pseudocode that I've written on the board, by the way, all of the explanation, that's actually been posted to Piazza as well. So if you can't see it up here, or if you've missed it, it's publicly available for everybody. So the problem I want to focus on is the traffic simulation. In this problem, if you haven't taken a look, just by show of hands, how many of you have not yet started A1? It's okay, I know you might be too embarrassed to admit to it, but remember, I was a CS undergrad once too. I know how it works. 12 hours before the deadline, yeah, I better get started, right? All right, anybody done? One person. Good job. All right, so the last problem on the assignment is a traffic light. So we have a four-way intersection, and there's a light that we want you to build effectively. So right now, only one car can go through the intersection at a time. If that was a real intersection, it would take you 10 hours to get from here to the McDonald's on King and Plum. Yeah, we'd like you to improve the flow of traffic through the intersection, but don't cause any accidents. So we've given you the following tools to implement better synchronization. You can use a lock that you just implemented. You can use condition variables that you hopefully just implemented as well. And you can use a semaphore. You cannot use weight channels directly. I don't advise using spin lock directly. So those are the tools that you have to try to improve the flow of traffic through this light. Now, because it's an intersection, and you know that, how many of you in here have driver's licenses? A good lot of you. So you're going to be very tempted to think, yeah, four-way intersection, I know how this works. These cars can go and these cars can go. And you know, in real life, they wouldn't cause an accident. Sure, but read the 3 rules at the bottom of the assignment, because we're not quite the same as a traffic intersection. And even if you think, okay, yeah, so we'll take away a few behaviors that normal traffic has, and you're like, I'll still implement it just like a real traffic light. If you're going down that road, you're going down the wrong road. Don't think of implementing this question as a real traffic light or a pseudo-real traffic light. You will not get an answer that is within the timing that we expect you to have. So it's going to be very tempting for you to have traffic coming from north-south and south-north at the same time. And technically, our rules state that that would not cause an accident in our system. But just because it doesn't cause an accident doesn't mean you have to permit it. Those rules are not saying how traffic must behave. They are saying these are the ways which accidents will not happen. You don't have to let all of those options even occur. One of the things to keep in mind is you're going to be thinking, okay, we've got north-south traffic and south-north traffic, and we've got east-west, west-east, and then we've got right turns, and we've got left turns. So you're going to be like, okay, so I'll have a condition variable for each of these things. No. That's too many. The amount of logic that you would need in order to manage 12 or 16 condition variables is way too much. You need a very few number of condition variables, a very few number of semaphores if you choose to go that path. Now, some things to think about. You need to keep track of who's in the intersection. Because obviously, when a new car arrives at the intersection, how do you decide whether or not it's going to cause an accident or not? A lot of people are very tempted to use the dynamic array class that is provided by OS 161. And yes, we have a dynamic array class that's built in. You can actually find the header for that in kern include array.h. And if you'd like to see how it is used, look in kern test array test.c. And that will show you actually how to use that dynamic array. And so what a lot of people do is when a car arrives, they'll check all of the conditions, all of the rules, and say, okay, this new car, does it cause an accident with any of the cars that are in this dynamic array that are currently in the intersection now? So compare, 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 compare. And if there's no accidents, you let it in and you add it to the array. And then as the cars leave the intersection, you find a copy of that car with that origin and that destination and you take it out of the array. And I know that's going to be your default thought of how should I implement this. But that's you thinking like a real intersection and you being a real driver. You can start with that solution if you don't see what the correct path is, but let me tell you, you probably will not meet our timing constraints if you do that path. Now you might meet some of them, but you probably won't get all of them. So to tell you about how my solution works, first off, my solution is something like 25 or 27 lines of code in total. And you know those 3 rules that are in the traffic simulation problem to determine whether a car is going to collide with another one? I don't check them. I don't check them at all. In fact, the destination, I don't even look at it. I have no accidents. I don't look at the destination at all. I don't have an array that keeps track of the cars in the intersection. I don't have a matrix that keeps track of the cars in the intersection. I'm not telling you how I do it, but that should be a pretty big hint. Think about it. Yeah?
I tried a similar implementation, but then I cannot decrease the maximum wait time.
So that's my next hint. How do you get the maximum wait time down? A lot of you are going to find that you have a solution and it seems to work and it sounds something similar to what I'm doing, but your maximum wait time is really, really, really big. And let me tell you how that happens. You have locks and condition variables, but you only need one lock. And you have some number of condition variables that I maybe won't tell you. And when a car arrives, you check to see if it can enter the intersection, and if it can, you let it go, and if it can't, you put it to sleep. And when it wakes back up, you recheck whether it can enter the intersection again. Here's the problem. Car was asleep. It's a really, really old car. It's been around since the beginning. It's asleep on a CV. The intersection is now empty. You broadcast your CVs to let some more cars into the intersection, and so it wakes up. But you have no control over what order that thread with that really old car is actually going to execute, and so it's entirely possible that the intersection empties again, and we let other cars in, and all of a sudden that really old car can't go through now, and so you have to check, and you put it back to sleep again. And you keep waking up that particular direction, and you keep putting it back to sleep again, and there's a really, really old car, and because you can't control the order of execution, that really, really old car keeps going back to sleep again, and again, and again. If you have cars that are going back to sleep, you're gonna have a really bad time. That is increasing your max wait time. You do not need a while loop. I don't have one.
I also don't tell, but it's still like exceed the maximum wait time.
You're still exceeding the maximum wait time even with no while loop. Maybe stop by office hours later. I haven't given you all the details. Now the next thing that you need to consider with the traffic simulation problem is when you want more cars to go through because the intersection is empty or whatever your condition is where you would let more cars through, which cars do you let through? If you're using the lock and condition variable approach, or you've got semaphores to keep track of this, which direction gets to go next? Which group of cars gets to go next? You have to think about that. Now some people will randomly select one. Some people will choose the one that has the most people waiting on it. Others choose the one that has the oldest car waiting on it. Some people just go in a cycle. There are lots of different ways that you can choose to wake up cars so that they get a chance to go through the intersection next. I'm going to leave it up to you to play around with all of those different options. I know which one I use, and it works pretty well, but I can't give you all the answers, okay? Now, another thing to keep in mind is that it's entirely possible that there's a whole bunch of cars coming north, south, north, south, north, south, north, south, north, south. And then a car that wants to go east, west shows up. When are you going to flip the light and let east, west through? Are you going to just keep letting north, south come until they're all done? Well, what if they come for the next 3 days? When a car arrives and it can't go through, in a real traffic light, if you actually look at the ground, there's actually plates in the pavement that can detect when a car is there. And once it detects a car is there, it sends a countdown in the actual traffic light, and when the countdown expires, the light gets flipped. Now, we don't want you to use timers, but there's other ways that you could actually do this. Like you could say either 3 more cars are allowed to go through, or the intersection empties, and then I flip the light. So there's lots of different things to consider for both fairness and decreasing max wait times. Now I'm going to post this to Piazza as well, but something to keep in mind is I know we've given you formulas for how much time we expect each simulation to run in, and you have no clue as to what values we're going to be passing to you. So I'm going to give you a few of our parameters. I will post this to Piazza later today, so that you have some idea as to the values for N, and K, and T that we are actually using to test your code. I'm not giving you all of them, but if you see the ones I give you, you can automatically infer the rest. We're not going to do a simulation with 1 car. That's dumb. I can't get any statistical information about your implementation out of a single car. Obviously, we're going to have some reasonable number of cars. So if you're testing your solution with 1 thread and 1 car, and you're like, oh, it doesn't meet the formula. Well, of course it doesn't. And we are aware of that, because we're not going to try that either. So I will post some numbers that we will use, and I want you to also know there is a teeny epsilon built into our system, so that you have to be within that epsilon of the actual formula value. I'm not telling you what the epsilon is, but it's very reasonable. So don't panic if you're like 0.001 over, 1/3 of the time that you run. The other thing I wanted to say about the grading of that particular problem is that there are part marks. So it's not an all or nothing. You either meet fairness and max wait time, or else you get marks for one and marks for the other separate. So even if you don't have the optimal solution, it doesn't mean you're going to get 0. You can still get part marks on that. And if you have more questions about how to do it, by all means, drop by office hours, and I'm more than happy to discuss where in your code you might be losing a lot of time. Any major questions? All right. Make sure, by the way, that you test your CDs and locks before you attempt it, though. So we left off last class, I'm going to switch over here, talking about semaphores and condition variables. Now, just to remind you of what they are, these are different synchronization primitives that we have to solve different concurrency problems. So, for example, we use semaphores. They can be used in many ways, and what they do, their big difference between a semaphore and a lock, is a lock has 1 resource. A semaphore can have any number of resources. It can have 0 resources, and we're responsible for adding resources at a later time. It can start out with n resources that people are going to take over time, and we can use semaphores for all different kinds of purposes. We can create a semaphore that behaves like a lock. That's a semaphore with 1 initial resource. You then P it before you V it. And to remind you what P and V are, P is the acquire resource, and V is the release resource function. And I know their names are horrible, and you'll probably mix them up for a little while until you get a little more familiar with them. But P is acquired, V is released with the semaphore. So we can use the semaphore as a lock, but keep in mind that it is not a lock. And even though we can use the binary semaphore to give us mutual exclusion, there's no built-in protections with the semaphore. There's no concept of ownership with the semaphore, which means that if somebody else tries to release my binary semaphore on me, they can. And then we end up with a race condition again. So it's on the programmer if they're going to use a binary semaphore to use it correctly. Then we have counting semaphores, of course, which is you are keeping count of a number of resources. And then we have things like the barrier semaphore, which is where we are going to force one thread to wait for all of the other threads to complete before we proceed. It's not separate implementations of the semaphore. It's all the same implementation. It's just we've attached names to different ways in which we use that particular that semaphore. Something else I want you to keep in mind is that the internal count value of a semaphore, you should never, ever access that counter directly. You can't just look inside the semaphore and see what the count is to decide what you're going to do. That count is a shared resource. And if you could just peek inside the semaphore structure and access the counter, well, somebody else might be trying to modify that counter at that point in time, in which case you now have a race condition. We do not touch the count of the semaphore outside of the P and V functions. Just don't do it. It's not safe. We will see more about semaphores when we talk about devices. All right, then we looked at condition variables. Condition variables are you are inside of a critical section and you really, really need a condition to be true before you can proceed. But the lock that you own is the lock that you are using to protect the shared variable that you need to have some other value. So you can't proceed and nobody can change the condition such that you could proceed. And what a condition variable lets us do is simultaneously, safely let go of the lock and fall asleep so that another thread can modify the condition and then wake us back up and we can proceed in our own critical section as if that never happened. Now, most of the time when we're using a condition variable, when we are woken back up again because the condition has changed, we need to recheck that condition. So we looked at producers and consumers, which if you remember, that is you have a finite buffer, you have a producer who's trying to put things into the buffer, and a consumer who's trying to take things out. The producer shouldn't have to wait for us, can't produce something if there's no spaces, and the consumer can't take anything if there's nothing to take. So when we solve this with a condition variable, our two conditions are the producer's waiting for the buffer to be not full. So when we wake up, because the buffer is now not full, we need to check to make sure when we actually run, that buffer is still not full. And the reason for this is there are other threads in the system, and in between the time we are signaled and moved from block to ready, another thread may run and make the buffer full again. So we have to check. You will see most of the time condition variables are used with the loop in this way.
So why don't we, instead of like creating condition variables inside the loop, just like lock it, check the condition, and then unlock it in yield? Isn't that the same effect?
Yeah, so that has, what you're talking about is actually on one of the previous slides here without the yield part. Let me go back to it here. You're talking about this solution here, except in between the release and the acquire you want to yield, which is going to force you, well, that's voluntarily giving up the CPU. Okay, yes, this technically works. Why is it bad?
Because it's slower, like it spins constantly or something?
Because it's spinning constantly. The problem is you are checking to see if the state has changed on repeat. Repeatedly, you give up the CPU, and then when you run again, because you're going from running back to ready, you reacquire the lock, recheck the situation, give it up again. So it's a spinning operation. And you are checking that regardless of whether the condition has changed its state or not. The advantage of using a condition variable over this particular implementation is with a condition variable, we only wake up and try to run because of a state change on the condition. We are otherwise blocked and sleeping. So it's more efficient to block than to spin like this, even with the yield.
So CPU wait blocks you, but yield keeps you ready?
Yield puts you in ready.
Okay.
CV weight blocks. So it's much better. Not to say you can't do it. One of the beautiful things about these synchronization primitives that we've given you is they truly are building blocks, and you can almost, you can solve any synchronization problem with any of them. That doesn't mean it's going to be efficient, but it is to say that you can almost interchange them anytime you want. All right. So that's an overview of the condition variables. Now, what I'd like to do now is show you the condition variable test inside of OS 161 so you're familiar with it for when you actually test assignment 1. So I'm going to switch over here to code. And I am in the wrong directory. I guess it isn't right. I'm going to go in kern thread sync.c. And actually, that's where our implementation of the CV is going to go. And if I show you that, then you'll have all the answers, right? Can't have that. So actually, I want to go into kern test, and in sync test.c, let me look up what line number it is here. So again, just to remind you, I know I should be making a vim init file. I've been telling myself that for like 25 years, and I still haven't done it, okay? Bear with me. So to keep in mind for this test, there are 3 global shared variables that are used by all of the synchronization tests. They are test val 1, test val 2, and test val 3. And then the synchronization test is on line 261. So this is CV test thread. And if you look at this code, it's not going to make a lot of sense. It's got these weights in here. Don't worry about that so much. Let me tell you what it does. So what it's going to do is that if test val 1 is not equal to the current thread number, it goes to sleep. That's what it's going to do. And then when it wakes back up, at the very bottom, what you see here is that we're going to change test val 1. We are going to set it to test val 1 plus the number of threads minus 1 modulo threads. That means that each thread is modifying test val 1, and we have to wait our turn until some other thread has set test val 1 to be equal to our thread number. Now again, probably doesn't make a lot of sense, but let me tell you what this test does. It forces the threads to sound off in reverse order 5 times. So what you should see is if you had 5 threads, well, there's too many here. If you had 3 threads, you should see thread 2, thread 1, thread 0, thread 2, thread 1, thread 0. Sounding off in reverse order. That is what we are expecting to see done 5 times. Now, to execute this test, this is SY3, and I cannot stress enough, until assignment 3, you absolutely cannot run tests back-to-back in OS 161. You must open the OS, run the test, and shut it down. Their implementation of memory has no free or memory management whatsoever. So you can't run tests back-to-back. And I know you're like, what do you mean there's no free? You still need to call it in your code, because if you don't, when it comes to assignment 3, and you have to fix free, if you haven't used free throughout your code, you're going to have a problem. Because we're going to take your RAM and we're going to do this to it and make sure that free works. So if you're not calling free, even though it does nothing, you'll have problems later on. So you can run the test from the command line. This is 161. And this is SY3. There we go. we have 32 threads standing off in reverse order 5 times. Again, we cannot give you some magical way to guarantee that your condition variables are implemented correctly, but you can be statistically certain that your condition variables work. So build a script, run this test between 100 and 1,000 times on a single core, and then once you're convinced that works, up the number of cores to 2 or 4 and run the test again. Don't run the tests on 2 or 4 cores to start with, because if there is a problem, it is an absolute nightmare to debug on multi-core, whereas it's a lot easier to debug on a single one. And I know it's not what you want to hear, that you have to write a script, but write a script. It'll save you. A couple other things I want to point out, and I'm going to make a Piazza post about this, common errors in OS 161 and how to debug them. And I'll try to remember to post that during my office hours here. But a couple things I do want to remind you of, aside from how to debug certain OS 161 mechanics, is you must initialize variables. You must initialize them. If I have a Boolean held in my lock and I don't initialize it in lock create, what value does it have? You don't know, and I don't know either. And sure, I have seen people make it all the way to assignment 3 and that not be an issue, and then on assignment 3, nothing works, and they're like, but I got perfect on the previous assignments. And I'm like, can you show me your lock implementation? And I realized that they forgot to initialize held to false or owner to null. You must initialize values. C does not specify what the initial value is. It's not, it says we don't care what it is. You must initialize it. If you have a spin lock, it must be initialized. If you have a Boolean, you must initialize it. If you have an integer, you must initialize it. You see the pattern here? Initialize your stuff. The other thing I want you to remember is that you cannot write to memory that you haven't allocated. If you are creating a spin lock that is not on the stack, i.e. you're creating a spin lock that is on the heap, you actually have to malloc the memory for it. And if you look at spin init or spin create, I'm pretty sure it doesn't malloc any memory. Be careful with your memory. Number one source of mistakes on the assignments in this course is people are writing to memory that they didn't allocate. This is not C shell you were working with. C shell had this thing which trained you to believe that when you compiled and ran your code, well, you didn't even see compiling. When you hit run, if you had memory leak or if you had some memory error, it would tell you about it. They'd be like, no, this doesn't work. That's C shell. It has Valgrind and an address sanitizer built into it. This is real world C. That shit ain't built in. And I'm sorry we don't have Valgrind working for 1.6 You are on your own. You must, except for the few rare circumstances we'll talk about much later in the course, you must allocate memory before you write to it. All right. So that's condition variables, hints. I'm going to post some more bug warnings from OS 161 later today because I've already seen some people posting to Piazza with them, and I'm not going to answer the same question 500 times. So I would like to then move on to talking about other kinds of race conditions. So if you remember, at the very beginning of this module, I mentioned there were 3 sources of race conditions. We have only talked about one, and that is your faults. It's code that you wrote, and you didn't either use synchronization primitives or you didn't use them correctly. It is a problem of your code, and as it turns out, there are 2 other sources of race conditions that are not your fault. Now, we only technically have to deal with one of them with OS 161, but let's talk about them. So as it turns out, CS241 has lied a lot to you, and so has CS251. They've both lied to you. First off, let's talk about compilers. So I know this course may have been a very long time for you, but when you compile code, it's not just a simple matter of taking the code, the C language, and translating it directly into assembly. We also do this thing called optimization. Because what we want to do is not just provide you with a direct translation of your C program in assembly. We actually want to give you the best performing piece of assembly code we could possibly give you. So compilers do optimization. You may have done a little bit of that in 241 if you had some time, or maybe you didn't get there. What we're trying to do is reduce, in general, the number of assembly instructions there are. Fewer instructions, fewer work done by the CPU. But we also really want to reduce the number of loads and stores that happen. Because loads and stores take way more cycles to complete than any other operation in assembly. How do we do that? Well, one of the ways that we can reduce the number of loads and stores is by making the following observation. If you look at a particular block of code and you see a bunch of variables are used, I'm going to go to the slide that actually has a picture of this. So let's suppose we have two functions. And they're both making use of a shared global variable called shared total. And inside of block of code func A, my compiler notices that, instead of going to RAM every single time to get the value of shared total, it would be much more efficient, and I have an extra register. Why don't I keep the up-to-date value of shared total in a register for the duration of the body of function A? This is called register allocation, and your compiler does this as part of its optimization. It is faster to do operations on registers than to retrieve things from RAM and work on it that way. And so register allocation, we're going to choose a register, and for a region of code, that variable's up-to-date value will live in that particular register. Here's the problem. Your compiler does not know about multi-threading. It does not know that function A could be run by multiple threads at the same time, and it doesn't know that function A, which uses shared total, and function B, which also uses shared total, could be running at the same time. So when it's doing the optimization of register allocation, it may say, for function A, let's put shared total in register 3, and for function B, I'll put shared total in register 8. A and B are now running at the same time. Who has the correct value for shared total? Register 3 or register 8? I don't know, and I know you don't know either, because the compiler doesn't know. The problem with register allocation is because it is not aware of multi-threading, we run into a big race condition. And this has nothing to do with you or anything you have done. Your compiler does all kinds of other things, so that is just one optimization that your compiler can do. There are others. Your compiler, as a part of its let's reduce the total number of instructions and loads and stores, also does instruction reordering to give us better performance. And as a result of things like instruction reordering and register allocation, and the fact that it doesn't know about multi-threading, your compiler just added a race condition to your perfectly sane code. Oops. Now, for this course, you do not need to worry about the reordering. Our compiler is old and dumb, but it does do register allocation. So, obviously that means we have the potential to cause race conditions. And as it turns out, there's also a way to disable it and force the compiler to always load that variable's value from RAM and store it immediately back in RAM every single time that particular variable is used, and prevent it from reordering the operations around said variables. If you would like to disable the register allocation optimization for a shared variable, you use the keyword volatile. And if you've looked at all of our examples through these slides so far, you will notice that every shared variable we have is volatile. We are not getting rid, we're not solving race conditions in our code by making things volatile. It doesn't solve a race condition. Volatile disables an optimization. That's all it does. It's going to disable the optimization. It's going to force the compiler to always get that variable's value from RAM instead of optimizing that variable into a register. That's all volatile does. When you have shared variables, make sure you are making them volatile. Now you might be wondering, well, some variables you don't need to make volatile, and that's okay. Could you make everything volatile? Go ahead. It's not going to break anything. It might slow your code down a fair bit. Good thing we don't care about that in this course. Yeah, so volatile, you have a global shared thing like an integer, like a process counter, or the hell variable in your lock, it should be volatile. Disable that optimization. All right, so your CPU does this. Yep.
So I see in the source code we don't use volatile for structures.
Because the structure doesn't change its location, but the individual fields inside of the structure are what we would be putting into the registers that would actually be being modified. So we would put the fields of the structure as volatile, not the structure itself. Because the structure doesn't change where it lives. That's not it doesn't move around. But the values of the fields will change, so they should be volatile. Yeah. All right. Now, that's not so we only have to worry about volatile. As it turns out, if you look at modern versions of C and C++, and by the way, we are using a version of C that predates all of you, I think. Is anyone here born before 2000? How about 98?
Does my 98 count within that range?
Sure. All right. Well, needless to say, all right, C99 was not released in 99. Because the C99 standard and the C89 standard are really, really old. They're roughly your age. Actually, they're older than that. They provide no protection aside from volatile for multi-threading. The latest versions of C and C++, the latest versions of Java, all have something called a memory model. And what the memory model is it is describing how threads have access to memory inside of a shared region. So inside any critical section, how do threads actually access the memory? And as part of the memory model, most languages actually provide their own built-in atomic functions. So they will have built-in locks or barriers that the compiler is now aware of. And when you use these functions and the compiler is compiling your code, it sees it and it's like, oh, this code here? Yeah, I shouldn't be optimizing it because multiple threads could go through here. So now we actually have the ability to tell the compiler, hey, this whole block of code, multi-threaded, and the compiler will know how to handle it now. That is built into modern versions of almost all languages. Unfortunately, our ancient version of C that we are using only has volatile. That's all we've got. Now, that's talking about the compiler. What about the CPU? We've always told you that the CPU has this fetch execute cycle. We fetch the instruction at the program counter, we decode it, we execute it, we increment PC, and we move on. Your CPU is way more sophisticated than that. It's got things like branch prediction and it does pipelining, and you know what else your CPU does? It also reorders the instructions. Because what we have realized is that the CPU can see, if it can know what loads and stores are upcoming, the CPU can rearrange them such that they will actually perform better. So your CPU is reordering loads and stores, which means your CPU just introduced a race condition into your code. So your CPU also has a memory model. And so that you can notify the CPU of, hey, multi-threaded code stuff going on here, your CPU has what's known as barrier or fence instructions to indicate when you reach the barrier or the fence, the entry gate. the CPU will be like, okay, I have to stop reordering stuff now, and then things will execute in the same order every time, and then when we reach the end gate, we turn all those optimizations back on. We are ensuring that every single of those instructions are always executed in exactly the order that they appear. So those barrier and fence instructions, they are assembly functions that are provided by the architectures. Do you need to worry about this with OS 161 and our MIPS R3000? Nope, you do not. The R3000 did not offer these functions because it didn't need to. But the R4000 did. But we don't have a 4000, so you don't need to worry about this. But if you are doing concurrency system level on a modern system, this is something you have to consider. And actually, if you'd like to see some of these memory models in greater detail, or if you're interested in seeing how to actually use these barrier instructions, I believe Ali's slides actually have some examples in them. And if you want to see some other examples, I'm more than happy to show you some examples from the Spark architecture, even though none of you have used Spark. All right. So we've talked about our two other sources of race conditions. And just looking at the time here. What I'd like to do now is, before we cover this last little bit on Deadlock, I'd like you, if you have that packet of handouts, there's one, or if you are on Piazza, there's one called in the handouts post Sem2CV. And I'll bring it up here on the screen as well. So this is Sem2CV. Take the next 6 to 8 minutes, work together. What I want you to do is look at this program that is using semaphores to provide synchronization. Try to convert this to using locks and condition variables. And if you're wondering, this is an old midterm problem. So this is exactly the kind of thing that you can expect to see on your exam. So take a few minutes and look at that, and then we'll look at some possible solutions. And again, if you don't have a copy of this in front of you right now, this is Sem2CV on the it's under the handouts post. Alright. So in order to solve this problem, one of the first things that you should do is look at what purpose each of those different semaphores actually has. And if you look at those, there's something special about two of those semaphores. What is special about semaphore A and semaphore B?
Yeah.
They're locks. So we can first off blindly replace those semaphores straight up with a lock. So let's do that. Let's just replace those with locks. So here we've got function 1. And I'm not going to do all the, the creation. You can figure out what variables I'm using as we go. So I'm going to acquire, see if I can spell, lock A, and then I will call function, see what it's called, function A, and then I release lock A. Alright, that's pretty straightforward. And then the other function here, function 2, we are going to acquire lock B. And then we'll call our function B. And then we release lock B. Now, the second, or the third semaphore, we actually use it so that the one function must wait for the other one. Question?
Oh, is it a condition variable? Acting as a condition variable?
No, condition variables have to be used with locks. Semaphore SC. That's when we need to replace the condition variable. Yeah. So we're going to need a lock and a condition variable. We are waiting. We see that function 1 is the consumer, and function 2 is the producer. And the initial count of that semaphore starts out at 0, which means that function 2 must execute once before the end of function 1 executes. So that last little bit, we don't terminate until function 2 has run before terminating function 1. So let's create a counter. I've got a count. Its initial value is 0, and I will make a CV, and I'll be boring, and I'll call it CV, and we'll make a third lock. Now, here's one possible way that you could solve this problem. I could say acquire lock C while the count is less than or equal to 0. CV wait on our CV, and we'll pass lock C, and then once we make up, then we decrement our counter again and release our lock. And then in function 2, I could do, acquire my lock. And then what I'm going to do is I produce my item. And then if the count is greater than 0, I call CV signal. All right, that's one possible way you could do it. signal, there's no point.
Yeah, well, you can always, like, as soon as you increment it, you're basically guaranteeing that it's going to be greater than 0 at that point.
But what if 10 func1s show up before any func2s? So the counter could be -10.
Except over there, they're always waiting for it to, oh, greater or equal to 0.
I think I have my count minus in the wrong spot. Just a minute. Let's put that count one more. There we go. Change things a little bit. This is one possible way that you can do this. No. We have not simulated the behavior of the original function like this. Didn't quite work. One of the problems that we actually have with this is that if there are 10 people who have come in and are waiting, then I have to wait for all 10 of them to go. For all 10 function 2s to show up before any function 1s get going. So that's a problem. There are other ways to do this, and in fact, I think if we put the counter down here, that changes everything. And there's even a way you can do this with just an if statement. So there's actually many, many different ways that you can do this. It's not that this one isn't synchronized. It's just that it doesn't mimic the behavior of the original function as it was intended. So I'm not going to write down the exact solution. What I'd like you to do is to go home and play around with the solution. I've given you one possibility that doesn't quite work the same way. Go home, see if you can fix it, and share it on Piazza, and we will let you know what's wrong with your options, or whether you have it right. I'm not saying no one's going to get it. There obviously are solutions that work, but they're not so obvious. So I do want you to spend some more time, now that you've seen a possibility that doesn't quite take us there, I'd like you to go home and actually try this. All right. One last topic to cover then. And let's put this slide down here. So, you got threads, which gave you race conditions. So we gave you synchronization primitives to stop the race conditions, control the order of execution of the thread somewhat. Now we have another problem. Each time we try to plug one hole, another leak sprouts. Now we have a problem known as deadlock. Let me explain how this works. Suppose you have these two functions here, and function A and function B both want to acquire the same locks. They want lock A, and they want lock B. Okay? But what if function A acquires those locks in the order AB, and function B acquires the locks in the order BA? So think about this order of execution. Let's say A goes first and it acquires lock A. So it has lock A, and before it can try to acquire lock B, there's a context switch. Remember, you have no control over where context switches occur. They can happen anywhere. So I have lock A, context switch now to thread B. Thread B now acquires lock B. Right? Context switch again, back to thread A. Thread A, which owns lock A, now tries to acquire lock B. But lock B is already owned. And so thread A goes to sleep on lock B's wake channel. When it goes to sleep, it owns lock A. When we go to sleep, there's an automatic context switch, so now thread B runs, and thread B tries to acquire lock A. But wait a minute, lock A is owned. So thread B goes to sleep, unlock A's wake channel. Who wakes them up? There's nobody that can wake you up. There is no magical prince that can come along, or princess, whatever you want, and wake you up. The operating system isn't even aware. The operating system doesn't know you've done something bad. These two threads are asleep forever. They will never wake up. Because the thread that owns lock A is asleep, so it can't release lock A. And the thread that owns lock B is asleep, so it can't release lock B. This is deadlock. You get to a point where you actually cannot make any more progress ever again. This would be like if in your lock acquire, you did not assert that you didn't own the lock already, and you tried to acquire a lock you already owned, you fall asleep on the wake channel of the lock you own. You never make any progress ever again. That's why I suggested you should put a case cert for that. Don't assume the programmer is smart. The problem with these synchronization primitives is that now that you are using them, you have to be careful not only to make sure you're using them to get rid of the race condition, but you have to make sure that you're not getting deadlocked at the same time. This is very bad. Very, very bad. And the interesting thing is you might think to yourself, and this is something I see in assignment A2A all the time, you think you have your race condition solved, and you think that you have no deadlock. And 99% of the time you run your A2A fork tests and your weight PID test, no problem. And then our TAs run it, and guess what? You had deadlock in your code. But deadlock doesn't show up every time it executes, because deadlock only shows up under certain orders of thread execution, certain positions of context which will cause the deadlock, whereas others won't have it. Deadlock is very, very difficult to detect, and it is very, very difficult in certain problems for you to prevent yourself from actually adding the problem. How would the operating system know to interfere? How does the operating system know that, oh wait, yeah, that thread's going to sleep forever, maybe we should do something about it? It just says, oh, you're asleep, I don't care. You're asleep in some wake channel, the OS is ignoring you. It's very, very difficult to detect the difference between a problematic wait and a wait for something on purpose. Maybe you really want the user to push the any key. Maybe they never push any key. How do you detect the difference between that and deadlock? It's actually quite difficult. Yes, that was a Simpsons reference, a very, very old one. All right. So we can't detect deadlock very easily. And there are many, many different ways that it shows up. Generally speaking, deadlock is going to happen when you have multiple threads that each require multiple resources. Now, there are some things that we as programmers can do to prevent from creating deadlock in our own code. Number one, don't try to acquire a lock you've already owned. Okay. If you did that K assertion, you got it covered. Number two, choose a deadlock prevention strategy for your code. Now, there are many different strategies you can employ. I'm going to present two of them to you. One of them is called no hold and wait. And what no hold and wait says, you may not wait while you own a resource. And when we say wait, we don't just mean you are not allowed to block while you own a resource. You are also not allowed to spin while you own a resource. Because there's also something called live lock, which is where threads are actually executing instructions but never actually making any progress. So, no hold and wait. What we need to do is we need to be able to acquire all of the resources at once. And if we cannot acquire all of the resources at once, then we have to release the ones we have and try again. In order to use no hold and wait, we actually need a special implementation of locks in order to support it. And I'm going to draw the pseudocode up here on the board. Let's turn these lights back on. I love this circuit breaker box. All right. So in order to implement no hold and wait, the trick about no hold and wait is that if you can't acquire the lock, you can't fall asleep. Because if you fall asleep and you own a resource, then you could get deadlock. So we need a special implementation of acquire. And it's called try acquire. Try acquire returns true if you get the lock. And if you can't have the lock, it returns false. But you do not go to sleep. So what we're going to do is we are going to acquire our spin lock. And now that we have the spin lock, it is safe for us to check whether the lock is owned or not. So if lock is held, we are going to, well, the lock is owned. So I am going to release the spin lock. And I return false. I did not get the lock. But if the lock is available, we don't need an else here. So if the lock is available, then what I'm going to do is take the lock. I release the spin lock now that I have taken the lock. And then I return true. There you go. And using this try acquire function, I can use no hold and wait to prevent deadlocks in my code. So the problem that we had on one of the previous slides, let's actually solve it using no hold and wait now. So I'm only going to show you the code for one of those functions, and you can infer it from the other. So what we're going to do is first, both of my threads want to acquire lock A and lock B. And they must, in no hold and wait, either own everything or nothing. So first, I own nothing. So I can safely call acquire. So I acquire A. Now I want to acquire B. But if I've gotten to the point where I'm trying to acquire B, I own A. I cannot fall asleep while I own A. So what I'm going to do while I am not able to acquire B, I'm going to release A, then acquire A again, and try again. And if you really want to improve the performance of this a little bit, you can put a yield in here. There. Deadlock solved. And it doesn't matter if I use this strategy, how many locks there are or what order I acquire them in. I either get them all or none. Now, one of the things is if you need to acquire a significant number of resources, the code to do that gets pretty complicated. You acquire the first one, and then you have to try to acquire the second one. Once you acquire the second one, now you have to try to acquire the third one. And if you can't get the third one, then you don't just release the previous one, you have to release the previous two. And if you're at resource 9 and you can't get resource 10, then you have to release the previous 9 resources. So the code actually gets pretty nasty to do this. And unfortunately, using the no hold and wait strategy also is going to impact your performance because I'm spinning. I'm spinning, trying to acquire everything or nothing. But it works. And you are welcome to try it. But I don't know about you, but I'm pretty lazy. option that requires no special implementation whatsoever, and it's called resource ordering. And here's how it works. You're going to assign every single resource a unique number. And then it is on you to make sure you always acquire resources in a strictly increasing order. So essentially what we're saying is when I need to acquire locks A and B, I must acquire them always A, B. Because it's when I have increasing and decreasing orders, that's where the deadlock comes from. If I always acquire them in a strictly increasing order, there's no deadlock. However, while that is very easy to do, it requires no extra coding effort, aside from making sure that you're acquiring the locks in the correct order, there is a problem. So you go to the University of Waterloo and you know that you're supposed to acquire those locks in a strictly increasing order. But you go to Google and for some reason there's a U of T person there and they're acquiring locks in a strictly decreasing order. Oops. It is on the programmer to make sure they leave appropriate documentation behind so that all developers know that the locks must be acquired in an increasing order. So it's now on you to make sure that everybody follows the rules. Otherwise, it's actually a really easy approach. So I'm going to leave that there for today. We will be moving on to a new topic next week.
Did you say that in the traffic simulation probably that it doesn't care about the destination of each one?
My solution doesn't even look at the destination.
Okay, could you post all of the hints on Piazza?
I will be, yes.
Okay, thanks.
Yes.